Good morning, everyone. We are the Group 7 and we will present to you our assigned experiment, which is the agitation. This is Daphne Prendas, and I'll be the one to discuss the introduction of agitation and its theory. So, the outline of our experiment will cover what is agitation, objectives of the experiment, procedure of the experiment, formula used, and data and calculation. So before I start the discussion, I just wanted to ask someone, what is your insight about agitation? Or when you hear the word agitation, what comes into your mind? So that is right. Agitation is the process of providing bulk motion to a liquid, thus aiding mixing and dispersion. Agitation of liquids is usually accomplished in a container equipped with an impeller, such as propeller, paddle, and turbine. For another question, many processing operations depend for their success on the effective agitation and mixing of fluids. Though often confused, agitation and mixing are not synonymous. So let me ask a volunteer if you have any idea on what is the difference between agitation and mixing. So that is right. The difference between agitation and mixing is that agitation is referred to the induced motion of a material in a specified way, usually in a circulatory pattern inside some sort of container, while mixing is the random distribution into and through one another of two or more initially separate phases. A single homogeneous material, such as a tank full of water, can be agitated, but it cannot be mixed until some other material such as quantity of hot water or some powdered solid is added to it. Liquids are agitated for a number of purposes depending on the objectives of the processing step. These purposes include suspending solid particles, blending miscible liquids, for example, methyl alcohol and water, dispersing a gas through the liquid in the form of small bubbles, dispersing a second liquid immiscible with the first to form an emulsion or suspension of fine drops, promoting heat transfer between the liquid and a coil or jacket. Often one agitator serves several purposes at the same time, as in the catalytic hydrogenation of a liquid. In a hydrogenation vessel, the hydrogen gas is dispersed through the liquid in which solid particles of catalyst are suspended, with the heat of reaction simultaneously removed by a cooling coil and jacket. Liquids are most often agitated in some kind of tank or vessel, usually cylindrical in form with a vertical axis. The top of the vessel may be open to air. More usually, it is closed. The proportions of the tank vary widely depending on the nature of the agitation problem. A standardized design, which is shown in the figure, however, is applicable in many situations. The tank bottom is round, not flat, to eliminate sharp corners or regions into which fluid currents would not penetrate. The liquid depth is approximately equal to the diameter of the tank. An impeller is mounted on an overhang shaft, for example, a shaft supported from above. The shaft is driven by a motor, sometimes directly connected to the shaft, but more often connected to it through a speed-reducing gearbox. Accessories such as inlet and outlet lines, coils, jacket, and wells for thermometers or other temperature measuring devices are usually included. Mechanical energy is required to rotate the impeller, which in turn transmits this energy to the fluid. Agitation in a process generally accomplishes physical changes, chemical changes, and or increased rate of transport and may occur simultaneously or in single. Agitation equipment usually consists of a tank to hold the liquid, one or more impellers to provide the shear flow, a motor or some other means to drive the impeller, and usually wall baffles wherein the installation permits higher power input. Impeller design has a strong impact on the agitation characteristics and the energy requirement in an agitator. Impeller agitators are divided into two classes, those that generate current parallel with the axis of the impeller shaft and those that generate currents in a tangential or radial direction. The first are called the axial flow impellers and the second is the radial flow impellers. So we have here a sample video of radial and axial flow from flow radial and axial impeller where we can see the difference between the two flow patterns. The three main types of impellers are propellers, paddles, and turbines. Each type includes many variations and subtypes. Other special impellers are also useful in certain situations, but the three main types solve perhaps 95% of all liquid agitation problems. One of the three main types of impeller is propeller. A propeller is an axial flow, high-speed impeller for liquids of low viscosity. Small propellers turn at full motor speed, either 1,150 or 1,750 rate per minute. Larger ones turn at 400 to 800 rate per minute. The flow currents leaving the impeller continue through liquid in a given direction until deflected by the floor or wall of the vessel. The highly turbulent swirling column of liquid leaving the impeller entrains stagnant liquid as it moves along, probably considerably more than an equivalent column from a stationary nozzle would. So the propeller blades vigorously cut or shear the liquid because of the persistence of the flow currents. Propeller agitators are effective in very large vessels. Another type of impeller is paddles. For the simpler problems, an effective agitator consists of a flat paddle turning on a vertical shaft. Two-bladed and four-bladed paddles are common. Sometimes the blades are pitched, more often they are vertical. Paddles turn at slow to moderate speed in the center of a vessel. They push the liquid radially and tangentially with almost no vertical motion at the impeller unless the blades are pitched. The currents they generate travel outward to the vessel wall and then either upward or downward. In deep tanks, several paddles are mounted, one above the other on the same shaft. In some designs, the blade conform to the shape of a dish or a hemispherical vessel so that they can scrape the surface or pass over it with close clearance. A paddle of this kind is known as anchor agitator. So the last main type of impeller is the turbines. There are a lot of designs of turbines and most of them resemble multi-bladed paddle agitators with short blades turning at high speeds on a shaft mounted centrally in a vessel. The blades may be straight or curved, pitched or vertical. The diameter of the impeller is smaller than with paddles, ranging from 30 to 50% of the diameter of the vessels. The type of flow in an agitated vessel depends on the type of impeller, the characteristics of the fluid, and the size and proportions of the tank, baffles, and agitator. The velocity of the fluid at any point in a tank has three components, and the overall flow pattern in a tank depends on the variations in these three velocity components from one point to another point. The first velocity component is radial and acts in a direction perpendicular to the shaft of the impeller. The second component is longitudinal and acts in the direction parallel with the shaft. The last component is tangential or rotational and acts in direction tangent to a circular path around the shaft. In the usual case of a vertical shaft, the radial and tangential components are in horizontal plane and the longitudinal component is vertical. The radial and longitudinal components are useful and provide the flow necessary for mixing action. When the shaft is vertical and centrally located in the tank, the tangential component is generally disadvantageous. The tangential flow of a liquid follows a circular path around the shaft and creates a vortex in the liquid. Exactly the same flow pattern would be observed with a pitch blade turbine or a propeller. So this type of flow is generally avoided in any type of agitation vessels in order to prevent any undesirable effect in the liquid which often results in the foaming, which is not good in the process. Circulatory flow and swirling can be prevented by any of three methods. In small tanks, the impeller can be mounted off-center. The shaft is moved away from the center line of the tank, then tilted in a plane perpendicular to the direction of the move. In larger tanks, the agitator may be mounted in the side of the tank with the shaft in a horizontal plane but at an angle with a radius. In large tanks with vertical agitator, the preferable method of reducing swirling is to install baffles which impede rotational flow without interfering with the two flow, which is the radial and the longitudinal flow. A simple and effective baffling is attained in installing vertical strip perpendicular to the wall of the tank. Baffles of this type are shown in the figure, except in the very large tanks. 4 baffles are sufficient to prevent swirling and vortex formation. Even one or two baffles, if cannot be used, have strong effect on the circular patterns. For turbines, the width of the baffle need to be more than 1/12 of the vessel diameter. For propellers, no more than 1/18 in the tank diameter is needed. With side entering inclined or off-centered propellers, baffles are not needed. Once the swirling is stopped, the specific flow pattern in the vessel depends on the type of the impeller.
Now what we have is the agitator rotating in the mixture, and this is a water mixture with flow following beads so that you can see what's happening. And essentially you have what we refer to as no top to bottom turnover. The material is pretty much just rotating in a big circle. And in this scale, you'll see a pretty significant vortex, which you wouldn't get in a larger scale. The vortex phenomenon reduces as the size of the tank gets bigger. So this is the nominal blending effect that you get with on-center mounted unbaffled tank, especially at relatively low viscosities. In the full scale, we're operating at about 200 centipoise under normal circumstances, and that still generates this kind of a flow pattern, even though the viscosity is up around 200 centipoise. Okay, now what we've done is we've changed tanks to one that has 4 baffles installed at 90 degrees to show the difference with dual axial flow impellers operating in a baffled tank. So we'll start the engine. Now you can see that we've got a perfectly well mixed tank with what we refer to as top to bottom turnover. In this case, solids that make it to the bottom of the tank are pushed down and back up the straight side and into the center again as you watch the flow pattern. This is an ideal back mixed flow pattern for producing the most efficient mixing that you can get with an on-center mounted agitator.
Good morning, everyone. This is Joanna Marie Rubin, and I'm going to present the objectives and procedure of this experiment. As you can see in this slide, the experiment has two main objectives and a sub-objective. So the experiment seeks to identify the effect of speed of rotation on power requirement for baffled and unbaffled tanks. It specifically aims to show the relationship between the power number against Reynolds number for baffled and unbaffled tanks. Second, to identify the effect of impeller diameter and power requirement of agitation on baffled and unbaffled tanks. So that's all for the objectives. Let us proceed to the procedure. These are the things to do in conducting the experiment. So first, fill the container to almost 14 inches. Do this in a tank without baffles. Next is to attach the impeller to the agitator. Third is immerse the impeller in water inside the container, such that its elevation is about 4 inches. After immersing the impeller, measure the power requirement for different speed of rotation with the dynamometer attached to the shaft, and measure the speed using the tachometer. To satisfy the given objectives, which is to determine the effects in an unbaffled and baffled tanks, place baffle strips in the container and repeat procedures 3 and 4 to obtain data for baffled tanks. And let's go for a little Q&A.
Good morning, this is Georgette Raponte, and I will be the one to discuss further about the materials and equipments and also the formulas used. So for the materials and equipments needed in the experiment, we have first the agitator, specifically stated as a two-blade paddle. An agitator is a device which is used to import motion in the form of steering to the liquids or semi-solids. The second one is the baffle strip. As what you've learned from the discussion and videos a while ago, baffle strip are internals, generally flat plates, used in agitated vessels to optimize and stabilize the mixing flow pattern and minimize variation in agitator power drop. Next are dynamometer and tachometer. So dynamometer is a device for measuring mechanical force or power transmitted by a rotating shaft. Thus, in the experiment, it measures the power requirement. Tachometer, on the other hand, is an instrument designed to measure the rotation speed of a shaft or disc. Thus, it measures the rotational speed. Now that you have learned the theory, objectives, materials, and procedures, we are now ready to proceed to the formulas. According to the book Transport Phenomena, there are 10 dimensionless numbers associated with agitation by heat and mass transfer. These are blend number, Froude number, Nusselt number, power number, Prandtl number, pumping number, Reynolds number, Schmidt number, Sherwood number, and Weber number. However, in this experiment, only the Reynolds number, power number, and Froude number will be used. Let's begin with the Reynolds number. It is defined by the formula NRE is equal to the impeller diameter squared times the impeller rotational speed times density divided by viscosity. Next is the power number, which is expressed as power number is equal to the power times a conversion factor divided by the rotational speed to the power of 3 times diameter to the power of 5 times density. Last, we have the Froude number, which is defined as NFR is equal to the rotational speed squared times diameter divided by acceleration due to gravity, which is 9.81 meters per second squared. In addition to that, we have this formula M is equal to A minus log base 10 NRE divided by B, in which A and B are constants that can be seen in table 9.9 provided in your screens. It must also be noted that in baffled systems where there is no center vortex formed, they are independent of Froude number.
Good morning everyone, my name is Sabin Rafael Pipito. I'm here to explain about the experimental data and sample calculation of my group. In our experiment, we have three sizes of impeller. Impeller 1 is 3.35 inches or 0.0889 meters. In impeller 2, we have 2.75 inches or 0.068985 meters. And impeller 3 has 2.25 inches or 0.05715 meters. For impeller 1, 2, and 3, we have made 3 trials with baffle and without baffle. The power and speed of each impeller were taken with baffle and without baffle. We have observed that for all the 3 trials of the 3 sizes of impeller with or without baffle, the power and speed are directly proportional. As the power decreases, so does the speed of the impeller decreases too. In the sample calculation, the figures for viscosity, density, conversion factor, and acceleration due to gravity were given. Constant numbers A and B for the calculation of shape factor are also given. For the calculation of without baffle, first we have to solve for Reynolds number. For the formula for Reynolds number is diameter over square. N is for speed from the experimental data, and you have to convert it into revolution per second. P is for the density, and N is divided by viscosity. Once you finish solving, the answer would be 34,839.4408. Then we proceed to the powers number. Big letter P is the power from the experimental data of trial 1, and GC is the conversion factor, and the power of 3 is the speed of the experimental data from trial 1. D to the power of 5 is the size of the impeller, and we have small letter b, which is the density. The answer would be 1.39 if you use the sample calculation. The answer for the power number is not the final answer yet. For without baffle, a vortex is formed. The presence of the vortex produces a smooth motion of the liquid, making the power number less. If there is a vortex, we use the NFR, or the Froude number, to multiply the power number. Then the MPO would increase because the effect of the vortex would disappear. Then we have to solve the NFR. The formula for the NFR is N squared times D over G. The N is the speed from the experimental data, D is the diameter, and G is the acceleration due to gravity. The answer would be 0.1395 once you input the data and solve it. Then we have to solve M, which is the shape factor. The formula for the shape factor is A minus log times NFR and over B. A and B is already constant. Once you input the number, the answer would be negative 0.088552. Then the last part would be solving the final power number. And the formula is initial power number, NFR, to the power of shape factor. Once you input the value, you'll get the answer 1.655, and that would be the final answer for the power number. In with baffle calculation, There is no vortex, so we don't need to solve for NFR or shape factor. We proceed solving Reynolds number and power number. Then we proceed solving the Reynolds number, d to the power of 2, which is the diameter, times speed times density divided by viscosity. Once you input the values, the answer will be 22,081.628. Then we have to solve the power number. The formula will be power, which you have to convert to joules per second. Gc is the conversion factor, divided by n to the power of 3, which is the speed, and d to the power of 5, the diameter, and small letter p is the density. Once you input the value, your answer will be 5.75. Since there's no vortex, we no longer need to solve for NFR or M. So that would be the final answer of power number.
Good morning once again, this is Charles Perez. So, in this part, we will now be watching some industrial applications of agitation. But before that, let us recap the basics of agitation in unbaffled and baffled tanks, and let us observe the behavior of the particles during the process. A center-mounted mixer in an unbaffled tank with axial flow impellers provides very little top-to-bottom flow, in which we can see the pellets were just swirling around the tank. And now, the primary flow pattern is rotating horizontally and a significant vortex develops. In addition, the heavier solids are not suspended and accumulate in the center of the tank, which we can see at the bottom. In a center-mounted agitator in a baffled tank, there is no vortex formation in the center, and there is a good top-to-bottom circulation and solid suspension, which is desired to have a higher mixing efficiency. So now let us proceed to the industrial agitators used in the industry.